Thank you, Danielle. Thank you to our three speakers. And let me look at the right screen. So let me start by taking hands up. I don't know if we want to continue with the question at the end of Eric's talk regarding why we can't completely tell the difference between binary black holes and neutron star black holes. Do we want to continue with that first?
Well, if there are no other questions, I would be really happy to hear more about this.
Actually, I can try and answer if you allow me, Eric.
Go ahead.
If you look at how we construct the template banks, we really look for like an order in the templates. We don't use random placement. We use some geometric placement. And in terms of the phase of the gravitational wave, there's only two measurables basically in this mass range. And these measurables are basically chirp mass and some combination of spin and mass ratio, okay? And the other measurables like tidal deformability and all of these are just, the response to them is too small. So evidence for a neutron star from tidal deformability is a very, it requires really, really high SNR. So if you ask, well, where does this affect? It affects from places in which the total of the SNR squared is much, much less than 1%. So you will have to have signals that are SNR, I don't know, 50, 100, 200 in order to even talk about this. So this is with respect to tidal deformability, and with respect to how to break the degeneracy between mass ratio and spin. So if you don't see the cutoff of, so there's another observable in principle that is not a phase measurement. It's actually a measurement of the cutoff frequency of the signal. So if the cutoff frequency of the signal is outside band, then you can't break the degeneracy between mass ratio and spin. Okay, so this breaks. So the total mass is the parameter that determines this cutoff frequency. So there's one actual signal in which there was an actual detection of the mass ratio. This is just a super coincidence in which it is at low mass enough in order for you to have two phase components that are well measured, and also high enough in, the cutoff frequency was low enough so that you have this measurement. So you have now three observables and three parameters and everything breaks. I hope I answered the question.
So actually, before moving across to somebody else, let me just kind of point out that GW 170817, where we did kind of manage to make some statements on the tidal deformability, had a signal to noise ratio of 30. So you don't necessarily need to go as high as 50 to 100. But one of the other reasons as well is that the templates that we use are based on a combination of post-Newtonian theory and numerical relativity. And your dominant effect is coming from the chirp mass, your next higher order effects are coming from the spins, and then at a much higher order level, you're basically getting the tidal deformability. And as Eric pointed out in his presentation, if the SNR is not large enough, then effectively the tidal deformability is swamped and we can't actually make a statement without having an electromagnetic counterpart. I think Robert had his hand up first, then Norma, then Elias.
Yeah, okay, thanks. It was for Barak. Could you please put up that graph again that you showed near the end? I think it was number versus chi-squared.
Okay, you have to tell me which graph.
It was near the end.
Near the end.
Maybe just go backwards. No.
This?
About the effect of spin, I think it was. Yeah, this one here. Yeah, no, you just passed it. It was the number, you had it there. It was two graphs side by side that were thin and vertical.
Two graphs side by side?
I think it's when you present the total number of sources at the end, where you have the cumulative distribution.
Yes, that's it. Yes.
Yes. So what's the question?
That one. Yeah. So I'm just trying to understand what you said I think you said there was no evidence for negative spin from this. I'm just trying to better understand why you said that.
I say the argument really slowly. So the negative side of the population is totally consistent with just having a population of binary black holes with zero effective spin. This is the statement. Everything else is, you know, a little bit more involved. But the negative side of the population is just dominated by having around 20 events out of the total 30 that have a zero effective spin.
Okay, but it's still possible there could be negative.
Oh, if 1 in 1,000 events has a negative spin, I would not be able to say that it does not exist. Okay, but I'm saying
Okay.
we have no evidence for a sizable fraction of the events having negative, having a isotropic spin distribution. This is the.
Okay, all right, thank you.
Okay, next up we have Norma.
Good afternoon, thank you. My question is for previous Eric, but any of you could answer. So please, Eric, about intermediate black holes, which is the formulation of the program for detection intermediate black holes? We know that now there are, I mean, candidates and some detections, and how you do you consider to take into account the correlation from what we have from X-rays observations, and now there is forthcoming research from Rosita, for instance, on the intermediate black holes. So I think that it comes to maturity to make to extend the picture, say, and to try to fill the gap, or at least to start to fill the gap for intermediate black holes.
So Nova, I'm not sure I got the first part of your question. I mean, what program you were referring to?
Well, the program you have, I mean, all programs you have now for observing black holes and intermediate black holes. I mean, how do you go for more detections on intermediate black holes?
Well, you know, we just take more observation, right? We take more data, and we hope to see more massive objects in the future. Related to what you say about electromagnetic observation, we are not. I mean, we are observing binaries, right? We are observing binary black holes, and the intermediate black hole that we've seen is the remnant of a merger of two black holes. Therefore, to connect to electromagnetic observation, you need some more global model, right?
Yes.
You need to make sure that all the black holes we are referring to are coming from the same processes, formation processes, and we see that probably there are multiple formation processes. So I don't think it probably belongs to LIGO and Virgo to decide on this. I think this is something that astronomers should take on and try to put all those information together, all those observations together.
Yes, but it becomes rather timely now to make all these correlations and multi-messenger. I mean, to extend the picture even for binary, intermediate, I mean, and for supermassive too. I mean, there are now a lot.
You know, Norma, the observation you were referring to earlier are probably intermediate mass black holes that are isolated, or maybe have a companion star, which is a normal star, and this is why you see it as a ULX, an ultra luminous X-ray, transient. But those are not the source we see, right? So there is little chance that multi-messenger observation will happen with those type of source.
Well, some binaries could be for your observations too. And for, I mean, for supermassive black holes, for instance, is and mergers or in all the states, it's very interesting to make the correlations.
So maybe I can say something. I'm like, because of the merger frequency of a gravitational of a compact binary is inversely proportional to its mass, then supermassive black holes are already out of the reach of ground-based detectors. You have to go into space to detect them. And basically the biggest limiting factor for us currently to search for intermediate mass black hole binaries is our ability to characterize and calibrate the detector at low frequencies. And this is one of the goals of future 3G detectors like Einstein telescope that will hopefully go down to maybe 2 or 3 hertz and will basically increase the mass range that we can search for. But currently, I don't think we're going to be seeing anything in the thousands of solar masses anytime soon.
Well, but it's interesting to make a groups, or I mean to formulate and to study, to well study the problem, because it would be a reach with, as you say, precisely in a space.
Okay, let's move on to Elias. Elias, if you're talking, you're muted.
I'm sorry. My first question is for Barak. I'm not sure if I understood correctly. When you apply your techniques, let's say to shift through the data, and you discover particular candidates, etc., what are the confidence levels at which, let's say you can attach to what you find, as compared, let's say, to the other cases?
Oh, that's a good question. Thank you for your question. With your permission, I will just skip to the slide. We are measuring the confidence of the events. Where is it? Okay, let's talk about this here. So, first of all, we are measuring the confidence of the events using time slides. So what does it mean, time slides? It means that we take the 2 detectors and we shift them relative to each other. And use these shifts in order to estimate what could happen just via pure coincidence between, let's say, a statistical fluke in Gaussian noise and then I don't know, a glitch in the other detector. Or maybe a glitch in one detector that picks a little bit of Gaussian noise and looks almost like a gravitational wave, which is actually the hardest thing to filter out. And then, in the other detector, some small contribution. So when you do this, when you take the detectors and you shift them one with respect to each other, and you repeat the entire process of detection, then what you get is this shaded, so you see in black here, this shaded, so these events, you have an exact knowledge of how frequently it is you see some event in this particular place.
Sorry, what do you have on the 2 axes?
This is the SNR squared in the Hanford detector, and this is the SNR squared in the Livingston.
I see.
Okay. So if you just add, A to B, then you have a detection line that looks like this. Okay. So this is our incoherent detection bar. And as you see, for example, this event, the negative spin event, is so far beyond noise that I don't even have any ability to measure how significant it is. It is as significant as this in this white area. Okay, so the LVC events are those. So for example, if you take GWTC1 and you ask what is the significance of this event according to LIGO, they say it's 1 in 100. But you can see from this diagram that this is so far into the thing that, okay, I can't even tell you how it's impossible basically to create this event via just a random shifting of the detectors. Okay, so we determine the reality of the events via basically the same method. And these events that we did declare are much less certain, much less, and we quantify as much as we can the probability for them being real events, and we report this in our paper. So I think this event, I can't commit that it's actually this one, but I think this event is like 50% real. Those two ones are like 70% real, and those two ones are like 98% real. Okay. So, and this one, probability 1. The other two events that we found are in here, and here you have to be much more careful about how you treat the background, okay? Because this is the loudest thing I've ever seen in Livingstone, and so time slides are not going to help me to understand what's going on unless you have something very clear in Hanford, okay? So this is either a glitch in Livingstone or a real signal. And then we operate something that we call phishing, which is a coherence score that is super tailored to fish very small response from the weak detector. And this particular event, okay, has some little but existent response from the Hanford detector, something that happens only 1 in 50. And we did measure the probability of this being astrophysical, and this is kind of 0.8 or something like this. Okay, but this probability is just our best estimate, and there's no real way to do this, you know, super quantitative to the bitter end, like you can do with time slides and when you have detections from 2 detectors.
But do you have an idea what made, let's say, one of the detectors have such a small sort of response?
So I know that about 10% of the events, so this is an injection study, so you can inject signals into the detectors, and Livingstone was a little bit more sensitive in O2 than Hanford. This is much more extreme in O3, but in O2, there were times in which there was an actual disparity between the detectors, and then events that you put also in a special place in the sky would have a very low response in Hanford, but an actual sizable response, like detectable sizable response in Livingstone.
So you're saying it's just purely statistical?
It's purely geometrical, let's put it this way.
I see. Okay, thank you. I have another question which is general, and it's addressed both to you and to Eric and whoever else can comment on it. Basically, I'm curious to know, what else do we expect to know from theory, let's say, in terms of shapes or other things, to improve basically this process of detection of gravitational waves?
So maybe I can take this. So if I had a little bit more time, I would have said that I think one of the major problems now in gravitational wave detection and also parameter estimation, more importantly in parameter estimation, is that the mass ratio range between, let's say, 3 and let's say 10 or 15, okay? The templates, when the spins are not aligned with the orbit, are not very good. So for example, the validity range of many different waveform approximates is just until mass ratio 4. And beyond that, hell breaks loose. And it actually happens in life that even if you put a signal that you should be able to model, when you try to do some parameter estimation, there's going to be some support of the posterior into higher mass ratios. And then you are going to be stuck with the bad feeling that you might have missed some physics of this, just because your waveform model is not good enough.
But can numerical GR answer in principle in this regime?
Maybe this is a question for someone else. So I'm not an expert in numerical GR. I just know that the existing waveform models do not support this.
Well, I remember that numerical GR has a problem when the ratio of the masses becomes big, but I don't know how big it has to become so that the numerics are difficult. Maybe you guys know it.
Maybe I can answer a little bit on this. So it depends on the complexity of your waveform. So if you're looking at a non-spinning template, so you don't have spins, you don't have tidal deformation, then I think you can, at the moment, I think we can go to a mass ratio of about 15. But as soon as you start putting other physical effects in, we don't have as many simulations coming from numerical relativity to build the templates. So as Barak said, for certain cases, if you want to have the most physical waveform available, you are essentially limited to a mass ratio of about 4. But at the same time, you know, if you're looking at binary neutron stars, we know that if the orbital separation is large, that post-Newtonian theory is still quite a good approximation for low velocity objects. So while there may not be the link with numerical relativity in terms of the high mass ratios, then, you know, you're in the early part of the inspiral, you're based on the validity limit of post-Newtonian theory when it comes to high mass ratios. And I think in that case, we're probably good to maybe a mass ratio of about 20.
So if, for example, if you take into account the results that Radu was presenting before, right now, up to the point where the merger happens, how far is it what you're saying, how far can you go in the mass ratio by using these types of analytical results?
I wouldn't want to kind of like bet next month's salary on it, but I'd say for you know, somewhere in the range of about maybe 10 to 15.
I see.
I was actually surprised that Radu did not mention this earlier in terms of you know, expansion in scope of those new approximate he was presenting.
Mm-hmm.
I don't know if there is any.
I don't know if he's around. Maybe
no,
he can.
he's not connected anymore. But right.
Mm-hmm.
And then if I can just say as well, if you want to do tests of general relativity, then we are severely limited by theory specific waveforms to high enough order in the phase to basically do kind of specific tests of general relativity. A lot of the waveforms that we're using are either putting unknown coefficients into the waveform phase, or taking something that we know about and putting something where you might expect dilatonic radiation or something like that. But we're still kind of we're still lacking theory specific waveforms for tests of general relativity.
But by this, you mean that people haven't worked out the full numerical problem from scratch, but they try to construct it in a sort of approximate form? I'm not sure if I understand why we're not having that.
If you take general relativity waveforms, and like even to develop post-Newtonian waveforms, it's taken about 25 years to get to 3.5 post-Newtonian order.
Oh, I see what you mean. I see. Mm-hmm.
Do we have any other questions, or does anybody else want to jump in with any comments on this? We still have about 15 minutes left for the discussion session.
So I can ask something. Sorry, I was in the middle of the lunch, which is the time for here. I have a question for anyone here who might have any comment on this. There was a paper, I think about a couple of weeks ago, claiming decisive evidence for primordial black holes from the distribution of binary black holes, which seems pretty a strong statement, but it did include some of the members of the LIGO collaboration. So does anybody have any comments on that?
Eric,
Yeah.
you read that paper?
So no, I'm sorry, I just read the abstract. I'm not able to comment more than this.
What are you talking about?
But what was the claim?
I think they were claiming evidence for primordial black holes from the distribution of LIGO binary black holes. I think as Salvatore Vitali was one of the co-authors, and
together with Antonio Riotto as well. So
they
were checking different distributions and very much as it was reported in Eric's talk, they were saying that the distribution with two different populations is preferred.
Yeah, but I guess the real question is, I mean, how do we know the astrophysical formation scenarios? I mean, do we know them well enough to preclude all of them and say that it must be primordial black hole? Yeah, I think the link Eric has posted it. Yeah, so that's that. It sounds a little bit very strong statement given the uncertainty in astrophysics. So I wonder if anyone has any comment about that.
No.
Yeah.
So I don't have any specific comment to that paper, but I have always a warning sign. We don't astrophysics. Like, you know, we as members of humankind, we are new in the game. We don't understand astrophysics well enough. And you know, if you had theories for solar system formation, when they were encountered with data, every single assumption they had made, oh, it's very obvious, or wrong, all of them, every single one. So let's be humble about this, and evidence for two populations does not imply immediately primordial black holes from inflation. So this is my take on it, but I don't have any particular comments on this particular paper. But I would say we don't know astrophysics. I think this is a fair statement.
So, I mean, I think this is a fascinating topic, and I mean, I do share your concerns, but I mean, it's interesting that this like a Pandora's box has been opened. But on a different topic that you mentioned, Barak, I have a question for you. So LIGO team also had an analysis of lensing, I mean, searches for possible lensing events, and I guess they didn't come up with anything. So I'm wondering, I mean, how do you, comparing your analysis with the LIGO team's analysis that they didn't find anything. I mean, what do you think? I mean, what's the difference?
So as you can see, there's a difference in every place. But to be more specific, first of all, the analysis of the pair, the analysis of the pair, we did it with a full joint parameter estimation that also included the phase information of the merger of the two bands, and we so-called the Morse phase. So there's a propagation effect for lensing, in which if you are observing something, some gravitational wave event that is observed through two different channels, the image types determine what phase you are going to measure from the gravitational wave. So if you have two images, let's say one of them is a minimum of the potential and another one is a saddle point, then there's going to be a phase difference of pi/4 in what you infer as the merger phase. If there's no higher modes, if there are higher modes, it's a little bit more complicated. So this particular effect, we also used it. And we did separate, so in order to try as much as we can not to count on the intrinsic parameters. So there's a like a complete there's a problem, there's a mess in this field in which when you have the intrinsic parameters agreeing, so what does it mean in terms of does it imply that they are more inclined to be copies of the same event or not? So if, for example, you believe that every mass can be and every spin can be, okay, then it's actually very surprising that you have two events that have exactly the same parameters to the precision in which 170104 and 170814 agree. But if, you know, it just so happens that astrophysics produces events with spin 0 all the time, and mass range is super preferred to have, you know, between 20 and 40 solar masses, then suddenly this is not surprising. You know, every set of 20 events would have a pair like this. Okay, so this is one thing that is a mystery. So we tried as much as we can to bound ourselves from this uncertainty by saying, okay, how many pairs have ever agreed on parameters, and let's treat this as a measurement of some astrophysical constant we don't know. Okay. And then we try to hinge the fact that they agree only on the geometrical parameters agreement, in which the prior is well known. Everybody knows that if they are on cosmological distances, then it should be isotropic in direction and orientation and all of this. Okay, so this is another difference between us and prior analysis. So this separation of intrinsic and extrinsic variables. And the last difference is that we also, so we measured like how improbable this is for a pair to exist in the catalog. And this is about 1 in 100 after bounding ourselves not to overinterpret the intrinsic parameters. And then we said, okay, 1 in 100, it's good enough to search for a third companion. And lo and behold, we found something that was actually the best candidate not to enter our original paper. So it was just one below the sub-threshold candidates we reported in the paper. And lo and behold, it agrees on the same parameter and sky position and Morse phase with the two events. So we were very, happy. Wow, it must be real. Like something happened to us, which is not something that happens every day. That So it's 1 in 100. So it's like you flip a coin and it stands on the side, and then you do it again and it again stands on the side. So we said, okay, fine. Let's try to treat this very, very seriously. And then when we tried to interpret the event, we figured out that the types of the events is something that is almost impossible to create with a decent gravitational mass that you want to have a lensing. So creating a maximum in this potential is something that is very hard and also not very observed in, let's say, lensing of optical, gravitational lensing is an old field, and we have many examples of multiple images of sources. And to the best of my knowledge, very rarely an H image has ever been measured. So this is evidence to the other side. And if you ask me, I don't know. I wouldn't bet no fraction of my salary for this being correct, or actually bet against it being correct. This 1 in 10,000 is, so I think the phrase in the paper is that we are left with no good solution of how this happened. So no satisfactory explanation. So this is my take on it. Okay. Do with it what you can.
I would add that, this is a very different type of lens because of the scale. So you don't necessarily, you shouldn't really bias your judgment by the cosmological, optical lenses, which are much bigger in size.
We hold this position for a few months, and then we tried to create a lens, literally play whatever you want. Create a lens with either 1 or 2 H images. And this was, I don't know, we failed. Okay, let's put it this way.
Cool.
Okay, do we have any further questions to our two speakers? We still have about 5 minutes left if anybody wants to ask any questions at all.
Okay, I have one last question. You advertised that you're hiring several times, but I couldn't find a link that I could point the students and postdocs to. So if you could share that somewhere. Should I just ask them to email you?
Yes.
Okay.
Okay, do we have anything else that anybody wants to ask or anybody wants to bring up or comment on? I'm not seeing any hands up in the chat, so I guess we're done with the discussion session. So let me thank our two speakers once again, and everybody for turning up. So thank you all.
Yeah, thanks, Ed, for doing this.
Thanks, everybody. Take care.
Everyone.
Good evening or
Bye.
good afternoon.
See you tomorrow.